So now we are in a position to discuss structure theorem of abelian groups. So which roughly says every finitely generated abelian group is a direct sum of finitely many cyclic groups or subgroups, maybe subgroups. This word subgroup I can drop groups. We will make it more precise later. And we need a definition, basically a concept to go for it. So this kind of thing, what I'm going to do is also already discussed in linear algebra, which normally people do in the first course of linear algebra in master's level. Let W1, W2, Wk be R submodules of an R module V. Then their sum is defined by those vectors in V which can be written as a sum of elements coming from these subgroups Wi. So ith member in the sum, ith term Wi is coming from capital Wi. So some of them may be 0. Which normally we call sum of subspaces. For groups, anyway, we have talked about something similar. And then we talked about direct sum or external direct sum. So, but this is happening inside a group, namely inside V. Right? In a vector space, we define what the sum of subspaces. Analogously, we are defining inside a module sum of submodules. Okay, and it is not difficult to show that this is a subspace of V. Verify that W1 plus W2 plus Wk is an R submodule of V. Okay. We say that V is a direct sum of subspaces or submodules. It is understood that I am talking about R submodules. W1, W2, Wk. If two properties I need, that V is the sum of these W1, W2, Wk. Secondly, they are independent. What are they? W1, W2, Wk. They are independent. What do I mean by this? That is, if I pick Wi from capital Wi, and there are some W1, small W1 plus small W2 up to on Wk is equal to 0, then only possibility we have is individually the Wi's are 0. Okay. So then we are saying that this is a V is a direct sum of the subspaces. So this concept we need, and you can recall that for a vector space V is a direct sum of subspaces if and only if V is a sum of the subspaces and their intersection is zero space for any W1, W2 subspaces of V. Such a thing we saw. But can anyone tell me, students can tell me that subspaces, I have the subspaces W1, W2, Wk of V, then V is a direct sum. V is a direct sum of these. Then if and only if, what is that? One is that V is a direct sum, is a sum of these. I should be able to write every vector like this. Sum of elements coming from Wi. And two, what is the analog of this property? Anybody would like to suggest?
Intersection of
Vi intersection Vj such that I is not equal to k.
Can you repeat? Please repeat.
Vi intersection Vj. Wi intersection Wj is equals to 0.
For I not equal to j.
For I not equal to j.
But is it enough?
P summation Wij for j not equals to I.
Okay, so this is a warning that this is not correct actually. Okay, so this I'll erase, replace by a similar thing, slightly stronger condition is required. Yes, please. What is the other choice?
Wi intersection sum Wj for
Wi intersection
sum.
W1, W2 like this.
Eliminating
Wi,
I.
yes, Wi I will remove. I am putting a hat above it. That means it is missing from the sum. Wk. So this should be what?
5. 0. I mean
0. Yes, 0 space. Right. So this should hold for each I. Right. On this range. Okay. So you see that this is a stronger condition than this one. This implies the other condition. If Wi intersects trivially some of the other subspaces, then you will intersect other individuals trivially. Can you give me an example where this condition holds, but this fails? The next one fails. What I have erased is true, but what I have included now is I mean, can you give example of W1, W2, W3 such that Wi intersection Wj is 0 for I not equal to j, but Wi intersection W1 plus W2 plus I mean, here writing that way is difficult. Let me call it Vi is 0. Vi is sum of W1, W2, W3, except wi. You know, one of them is missing. Okay. So can you suggest me an example?
1001.
So what is your whole space? R2?
Right. Yes.
R2. Fine.
So the second condition you took, but vi intersection vi is equal to 0. It's not equal to 0, I think. You mean by that?
No. See, here, vi means wi is missing in that sum. Okay.
Yes, sir, yes. Sir. But sir, we are looking for counter example. Like we have already
Yeah.
taken wi
Yes,
intersection wj
Correct.
0.
Correct. But this is true, but this is not true. So I'll
Yes,
cut cross it. That is right.
Yes, sir. Yes, sir.
Yeah. This is what you mean. Fine.
Yes, sir.
Yes. What is your W1?
Span of 1 0, then 0 1 and 1 1.
Span of 1 0. X-axis?
Yes.
X-axis. W2?
The y-axis
Y-axis.
and the line x equals 1.
Okay. All right. So here, certainly, the first condition, there are 3 conditions, all are satisfied. And whereas when we take sum of any 2 of them, we get whole space. So this is also true. I mean, this equal to 0 is false. Right. So therefore, we should remember this one. All right. Sometimes we ignore, so therefore to be careful. All right. So I can go ahead now. So now we are going to talk about direct sum of subgroups of an abelian group. Because already in the beginning we have stated roughly a finitely generated abelian group is a sum of cyclic groups. So now the theorem I'll state more precisely, theorem, which is structure theorem. A finitely generated abelian group V is a direct sum of cyclic subgroups CD1. So D1 is the size actually. CD1, CD2, CDK, and a free abelian group L of finite rank that is this V is isomorphic to CD1, CD2, CDK, and direct sum with free abelian group of finite rank, where the order di of CDI. When I am saying CDI, cyclic group of order di, which is same isomorphic to Z mod diz, or which is sometimes also called Z di, right? Is greater than 1. Trivial group I don't have to consider. And each di divides the next di. That means di plus 1 for I from 1 to k minus 1. Is the statement clear? So this is about how it is going to look like. Next question can be, can I have a different form like CD1 prime, CD2 prime like this, CDK prime, direct sum with L prime, where L and L prime may have different ranks, D1, D2, D. I mean, they are also, I'm assuming that Di prime divides Di prime, Di plus 1 prime. But can I have Di different from Di prime, etc.? So that is another question which we have to answer. So which is called uniqueness of this form. Actually, the answer is yes, the statement is true. But now we are stating how it is going to look like, and that this form is unique is another statement which we are going to see later. All right, so now we have to prove this. If you have a question about this statement, please ask. If you have no questions, I'll go for proof. Okay. So quickly, I recall how to start something which we have already done. Suppose V is generated by V1 to Vm. Okay, it is generated by V1, V2, Vm. So V1, V2, Vm are elements belonging to V, and every element is a Z linear combination of these, right? That is, we have a surjective map from Zm to V. What is the map? That x1, x2, xm is sent to the combination xi vi, I equal to 1 to m. And this is a surjective or homomorphism of abelian groups, right? All right, so it may have some kernel. The kernel W of this homomorphism is a finitely generated, is a free, sorry, let me just write free also, free. So Z is a Noetherian, Zn is free, Zm is free, and therefore its submodules are finitely generated and free. Is it fine? Z is Noetherian. So every submodule of Zm is free and finitely generated. This we proved. And we initially left one part of the proof saying that let us assume, at that time we said we assume that submodule is finitely generated. So later we showed that for a Noetherian ring, submodule of a finitely generated module is finitely generated, right? Okay, so then what? Suppose W is generated by W1, W2, Wn. Certain things I am repeating because there was some confusion which I understood. Some people asked questions. So at the time I said that while discussing the structure theorem, I'm going to repeat it. So that's why I'm repeating some of the arguments. So now, so what I have, that I have a, therefore, since W is generated by this, so that what I can say, the map from Zn to W, any x1, x2, xn, map to summation xi wi, I equal to 1 to n, is a surjective homomorphism. Okay, So by first isomorphism theorem, I apply here, and what am I going to get? So V, the group I have in my hands, is isomorphic to Zm upon the kernel, which is W, and it is isomorphic to Zm upon what is that W? You see, W is a sub of Zm, and I have a matrix whose linear map, therefore a matrix which when I apply to elements of Zn, I get whole of W. So what is A? So where Aij is given by Wj equal to summation Aij Ej. Ei, sorry. I equal to 1 to M. Right? So if you like, you write Ej, or you want to write this is fine. It's fine. So this is what we were talking about, that if I want to understand a finitely generated group, I need to know what A is. Okay. Thus, we get the presentation matrix of V. So if I know presentation matrix of V, then I know V, because then I can say that V is isomorphic to Zm upon Azn. Okay. So, okay, A belongs to how many? M by N? It is okay. Is there any confusion now? Please let me know before I proceed. No, nobody would like to say anything? At least you don't have any confusion. Is it okay?
No, sir. Please continue.
All right, fine. So now we'll try to change basis and write A in the diagonal form. Okay. That is what I'm going to write. Use diagonalization. And write without loss of generality. That means I'll change the matrix, then I'll get an isomorphic group. Okay. I'll say that A is what? Diagonal. D1, D2, like this, DK. Then I may get some, columns, 0 columns. I may have some 0 rows. Where DIs are natural numbers, but different from 1. If some negative is there, I can multiply by -1. If I have 1, say D1 equal to 1, then I'll say that I'll drop the row and column, first row and first column. Right? This kind of discussion we had already. And DI divides DI plus 1 for I from 1 to K minus 1. Thus, V is generated by V1, V2, like this, VK, VK plus 1, VM. So already we have discussed that such 0 columns I can drop. Okay, so without loss of generality, I can actually drop and then write down A. Okay, 0 relation I don't need. There is no use of any 0 relation. 0 equal to 0 is not a condition. It is tautology. It is always true. identity. Okay, so generated by these elements with relations. Now, how the relations look? Di Vi equal to 0 for I 1 to k. So we have a condition for from 1 to k. That means d1 v1 equal to 0, d2 v2 equal to 0, like this, dk vk equal to 0. After that, there is no condition, right? So vk plus 1 up to vm, they do not have to satisfy any condition. They are free. Okay. Suppose Cj is this group, is denoted by, is the group generated by Vj. Then Cj is isomorphic to Z upon djz. I want to say that, I mean, this Cj, okay, I mean, Cj is actually dj, C of dj. Here the notation is C of dj actually. Okay. Maybe that is what I write. Let me write this rather than writing j. dj is better. When we write, I mean this. Okay. And this is for j equal to 1 to k only. And Cj is isomorphic to Z for j equal to k plus 1 to m. Okay. Set this L to be sum of C. Okay. I mean, this again, I'm sorry that this dj is again troubling some problem to me. So let me write j only. J only. Yeah. So the reason why I'm trouble with dj, because when j is bigger than k, this Cj is C of not any d, no dj. It is the infinite cyclic group Z, right? So let me just stick to this notation. This is not by mistake only. This is not by mistake. So this is deliberate. And yeah. So what is L? L is from j equal to k plus 1 to m. So this may be empty collection. In that case, L will be 0. Okay. Which is same thing as Z m minus k. For k equal to m, L is the 0 group. All right. So then V is the sum of Vj. Oh, so this is a different notation. Yeah, better to use a different notation rather than calling the C Vj. Sorry. Yeah, why? What is the problem that writing Cj? Because I'm writing C dj. So Cj and C dj, they are confusing. So let us call them as Vj. Capital Vj for the space. Yeah. So now we have to show that this sum is actually direct. It is a direct sum. So every element in V is a sum of elements coming from Vj. That's not a problem, that you have understood. Suppose summation Wj equal to 0 for j equal to 1 to m, where Wj is picked from Vj. So let us note this as star. So what I know, this Wj is Yj Vj for okay. Since Vj is generated by small vj. So every element is a multiple of vj. So star becomes summation Vj, Yj equal to 0, j equal to 1 to m, which can be thought now as B generating element V1, V2, Vm to be in B and multiplied to the column Y, and this is 0. Since columns of A form a complete set of relations, any relation is a linear combinations of the columns of A. This Y is Ax. Okay, any element in any Y here is Ax. Okay, this is what we are saying. A complete set of relations. Okay. For x belonging to xn. So what is there for Yj? So Yj is Dj Rj for Rj belonging to Z if j is from 1 to k. You see here, for what is my A? This is my A. So up to k, these Yj's are Dj multiple. And after that, I have just 0 for if j is bigger than or equal to k plus 1. Since dj vj is 0 for j equal to 1 to k, I can combine by these two what? That each wj is 0. This is what I had to show, that the sum is 0 implies each wj is 0. So we have done this. Thus, the sum v1, v2, vm is direct. So v is a direct sum of these. That is what we wanted. If you have a question, you can ask now. Remark. If A and B are natural numbers, are co-prime, then CAB is isomorphic to CA with plus CB. Is it fine? For example, C2 plus C3 is isomorphic to C6. But C2 direct sum with C2 itself is not isomorphic to C4 or similar, or C2 with C4 is not isomorphic to C8. Anybody would like to suggest me a reason why they are not isomorphic? This, for example, why this is true?
Element of order 4.
Element of order 4, correct. In the right hand side group has an element of order 4, but the group in the left hand side does not have any. Whereas there are 3 elements of order 2 in the left hand side, and there is only 1 element of order 2. How many elements of order 2 are here in C4?
1.
Only 1. In C8, how many elements of order 2?
1.
1. Is it fine to everyone?
Yes, sir.
Yes, sir.
Oh, okay, fine. Good. So the number of elements of order dividing 2 in C2, in C2 square and C2 cube are, till complete this one, number of elements of order dividing 2. That means 1 is also allowed. Now 1 and 2 basically. How many elements are there of order 1 and 2 in C2? Answer is 2, right? For C2 this is, I will not ask. Even C2 square, that means in C4.
4.
4. How many elements are there of order 1 and 2?
1, 3, 2, 4, 3.
Only
One
Order
over
element
one.
of this.
One element.
Only
And
this
two
one I'm asking now.
So
How
two
many
elements,
elements
it
are
is
there?
C4, na?
Yes, in C4, that is right. It is C4 only.
2 elements. 2.
There are 2 elements, namely trivial element and the unique element you said, no? There is only 1 element of order 2 here.
Right.
So
sir.
there are exactly 2 elements of this type, that order divides order of the group. Or sorry, divides the number 2. In C8, how
Same.
many elements are there of order?
2.
2. So this answer is 2 only. So when I'm increasing the size of the group, this number is not changing. Okay. We are trying to observe something and then we will generalize. The number of elements of order dividing 2 square in C2, C2 square and C2 cube are. Now can you again complete? What are the 3 numbers? They are equal, different.
Different. They are different.
Different, correct. For C2, tell me for C2.
0. Sorry. 1.
No,
1.
order dividing 4.
2.
2.
2, all elements, right? 2, correct. Comma,
4.
4,
4.
correct. 4. Then
8.
Here also 4.
here also 4. So this is why I'm asking you.
Right.
See, whoever is answering wrongly, it is not that they do not know. So there is a illusion kind of thing. So you have to be careful, because I'm saying order dividing, right?
Right.
So this number, 4 now in the present one. So if I raise it to 8, then okay. So if I raise this number to everything is same, then I'm writing 2 cube in C2, C2 square and C2 cube. Then what are the 3 numbers?
2, 4, 8.
2,
4.
4, 8. Now change.
That's right. Okay, so I just want you to observe this pattern, how this counting of elements of order dividing some prime power, how it is changing in the cyclic groups. So it's just want to write more generally. You see that it is nothing to do with 2, right? I can replace 2 by P. Is it okay?
Yes, sir.
More generally, the number of elements of order dividing P to the power I in the group, cyclic group, P to the power J is given by. Can you give me a formula now for this number? Here all are same. Here 2 of them are same. Here they are distinct. Why this is changing? There is something to do with what is the number that order should divide and the order of the group, cyclic group.
I and J.
Yeah, anything are you going to suggest? What is this number? P power something will be the answer. Can I say at
Right.
least it is some p power? Okay,
Yes,
some p
sir.
power.
Yes, sir.
Do you agree?
Prime power.
Yes, p power. Because I am taking p is the prime. So it cannot exceed p power j. Right? Total number is maximum is p power j. So it is p power j if j is smaller than equal to I. Do you agree to this?
Yes,
If
sir.
I is very large, but group size is just p power j. But I am talking about order dividing p power I. So that means every element will satisfy. So this is not a big deal. How about if I is less than j? What is this number? You are very close to the answer, right? Just one more number you have to write. And you see the above examples. When this number is 2, you had 2. This number is 4,
Prime power j. I.
p power I?
Yep.
Yeah. P power I. Is okay because you have enough elements. You have p power I elements are there in p power C, p power j. Is it fine? Do you agree to this now, this formula? I mean, you can verify this, you can carefully spend some time and verify. But this pattern, you can observe in a few and then you can generalize, not a problem. Okay. So if you have any, want to discuss anything, we can here discuss, or then I'll go ahead. Okay, fine. So after this observation, if you like, you can call it a lemma. So what I'm going to do, maybe you can call it a lemma. This more generally I'm pushing up. So this is our lemma. And then this to be capital. All right. So I'll say that another form of the structure theorem of finitely generated abelian group. So this is another version. Every finitely generated abelian group is a direct sum of cyclic groups of prime power order, and it's and of course a free group may be there. So therefore I'll write finite abelian group. Okay. If it is finitely generated, I can have a free part. Okay. Every finite abelian group is a direct sum of cyclic groups of prime power orders. So we know we are given any whatever the order is. So I have a prime factorization. So note that what this, if d is a natural number, then d I can write as product of primes pi, I equal to 1 to say k, and these primes may be repeated. So let me give some indices are I, and hence I have CD is isomorphic to. Please tell me what I'm supposed to write now. Cyclic group of order D, and I have the decomposition, prime decomposition here as a product of prime powers. What am I going to write?
It's
C
PIR.
P I R I product.
C P I
P
R I.
product.
Okay, maybe I write direct sum notation here.
Direct.
Right. I equal to 1 to k. All right. So this is one observation. Theorem. So yeah, this comment I could make when I was talking about 2, 3, this one. Oh, long back, I think I talked about it. Yeah. So this theorem is for uniqueness. Suppose that a finite abelian group V is a direct sum of cyclic groups of prime power orders. Say dj equal to, now my definition of dj has changed. Okay, previously I said di divides di plus 1. I did not assume anything about how whether di is a prime power or not. It could have it could be product of more than one prime, maybe some of them repeated. But now I am writing dj equal to pj to the power rj, where pj is a prime. Okay, so this is assumed. Then the integers dj, sorry, yeah, are uniquely determined by the group. So that means given a group and a decomposition like this, you cannot change the size of the cyclic groups if their orders are already prime powers. Then you cannot change the prime power. So to understand this, let us see an example. So which we have just seen in the beginning. C2, suppose I have C2 direct sum C2, which I can write it 2C2, right? So once I have this one, I have another group of order 4. I cannot change it. Okay. Yeah, maybe, you know, what else? Any confusion about the statement? Okay, maybe we'll see more examples after the proof. Proof takes a little bit of effort, although not very long. Let P be one of the primes that divides okay, or I can say that appears in the direct sum decomposition, because I am starting with a decomposition and we want to say that you don't have another choice of V. Suppose, sorry, small ci is the number of cyclic groups of order p power I in the decomposition. For example, here in this example, here the number is 2. So C1 is 2, P equal to 2, and then small c1 is 2, because 2 power 1. So whereas in C4, C1 is 0, C2 is 1. Right? There is only one copy of C4, no copy of C2. Here there are 2 copies of C2 and no copies of C4. Okay. So is it okay? Definition of CI? Is the definition of this number CI or parameter CI is clear? The set of elements whose order divides B power I is a subgroup of V. Is it okay? Set of elements whose orders divide P power I. They form a subgroup of V. That subgroup, which is a P group. That subgroup, it has to be a P group because the P is the only prime that divides the order of any element. Say of order P power Li. Some order will be there. I am giving a name to that index Li. And further, suppose K is the highest index of P such that the number of copy is positive. After this, there is no copy of cyclic group of order P power K plus 1. Okay, P power K, there are CK copies. So what do I mean by all these? That is the cyclic groups of order P powers contribute what in the decomposition as what? C1 Z, or you can write C1 CP direct sum C2 CP square like this, CK CPK. Is it okay? C1 may be 0, but CK is non-zero. Okay. Then P power L1 is equal to P power C1 times P power C2 P power CK. Do you agree now? Already we have in the lemma how many elements in CP of order dividing P. That is, answer is P. So since I have C1 copies, so there are exactly P to the power C1 elements. Here, from here, similarly, I'll have P elements exactly, whose order divide divide P. So number is P again. So since there are C2 copies, I'll have exactly P to the power C2 such from here. So together I'll just multiply and get total number of elements in that subgroup. So this is important. After this, P to the power L2, anybody can tell me here number of elements of whose order divides P square. What is the number of elements? It is P to the power L2, and therefore it is equal to what is the contribution of CP? Again, P to the power C1. What is the contribution of CP square? Anybody? I thought you have understood that argument. It will be P square. So it will be 2C2. Right? Order dividing P square is from CP square, there are P square elements. So therefore, from C2 P square, there are P to the power 2 C2 elements like this. p to the power 2ck. So if I proceed like this, L3 p to the power c1, p to the power 2c2, p to the power 3c3.
3C.
Correct.
Continue.
Then p to the power 3ck.
3C.
What is the last thing? P to the power lk is pc1, p2c2, p3c3, like this. Last but one, let me write k minus 1, c k minus 1, p k c k. Is it okay?
Yes, sir.
Yeah. So this is that what I call lemma. I have just applied on individually these groups, and then to get all elements, I have just multiplied because it is an abelian group. So this will order I can find like this. All right. So what I can write, L1 equal to C1 plus C2 plus dot dot CK. Then L2 equal to C1 plus 2C2 plus dot dot 2CK. L3 is C1 plus 2C2 plus 3C3 plus dot dot 3CK. Like this, I'll have last LK C1 plus C2, sorry, 2C2 plus dot dot K minus 1 CK minus 1 plus KCK, right? So what I have now, I have a system of equations as if, right? Okay, so coefficient matrix I am writing first. 1, 1, 1, like this, 1, 1. Then 1, 2, 2, 2, 2. Then 1, 2, 3, 3, 3. Is it okay? That is, I am writing the same thing, right? 1, 2, 3, k minus 1, k. This, when I multiply to C1, C2, CK, I am supposed to get L1, L2, LK. Am I right? What I have got here, these relations I have converted into a linear algebra question. Okay. So C1, C2, CK, this k tuple is uniquely determined by L1, L2, LK. See, L1, L2, LK, they are coming from the group. They I cannot change. If you give me a group, these numbers are fixed. Now question is, can I have a different presentation? Like, you know, coefficients for in this C1, C2, small c1, small c2, small ck. I cannot if they are uniquely decided by L1, L2, L2 up to LK. Are they uniquely decided by this K? Answer is yes. Because, can you tell me because what? The coefficient matrix is row equivalent to what? Can you tell me what is the obvious one? 0, 1, 1, 1, 1. I just subtract the second row from the first. Then 0, 0, 1, 1, 1. I subtract the second one from the third. Like this, 0, 0, 0, 0, 1. And this is invertible, which is invertible. Therefore, C1, C2, CK are completely decided by just simply taking this inverse. Take the inverse, right? L1, L2, LK will decide what are C1, C2, CK. I do not have a choice other than what is given. Okay. So therefore, this uniqueness statement is done. Okay. How many copies are there of prime power order? If I know one form, that is the only possible form. Only possible form meaning decomposition into product into the sum of direct sum of cyclic groups of prime power order. Okay. If you have any confusion, you can ask now in these arguments. Anywhere in the proof, if you have any doubts, you can ask. Time is over, so I'll finish after this. Then I'll say why, one more thing I need to say, complete actually do this, that if d1, di divides di plus 1 in the previous structure theorem, finitely generated argument, there it is also unique. Maybe a few example I have to give and then you will understand. I'll do that in the next class. I'll start with that because then you may have some doubts, we can discuss. Any questions? Okay, so I'll finish then here. Yeah, please close now.
Hello, can you show once the Ritumoni?
Yes, please. Do you want me to share again?
Yeah.
Okay.
Just I will ask one question to students.
Yeah.
Last slide, that matrix. It is
Yes.
not related to this subject, but little different.
Yes.
So somebody can tell you the matrix. How do you get that directly? Irrespective of the what's are taught today. Can somebody tell me this matrix? How do you get? What is aij entry? Ij, right? What is ijth entry? Okay.
Yeah. Can you describe the matrix? Sorry is asking whether you can describe by the matrix by just saying that what is the ijth entry. For example, when I equal to j. If it is I equal to j.
When I equals to j and these are 1.
If
Not
I
one.
is greater than j,
No, I equal to j, it is not 1. In the first matrix, na?
Yeah,
The first
first
matrix. This matrix.
yeah.
It is I.
Yes, it is I. Correct. Then you describe.
Okay, so because time is up, so can you look at minimum of ij? Ij minimum of I comma j. These are called minimum matrices. Okay.
Presentation.
Deepak, you are saying something. Can you say loudly? Okay.
No, sir.
So I less than j. So is
Aij equals to
Minimum of I comma j.
I or minimum of I comma j.
Right? And
Right.
you can easily check that what is the transpose of the last matrix, right? You see the transpose of the last matrix and multiply to itself. What you get, that also try to understand. That becomes LU decomposition. This matrix is symmetric and it is a positive semi-definite also. Determinant anyhow 1, right? That also you can easily see. So many properties will be there for these minimum matrices. Okay, just I want to add that point.
Yeah, thank you. That's a nice one.
Thank you,
So
sir.
should I now close?
Yeah, right.
Okay.